Did you want to show the website or something? Huh? Did you want to show the website? Good morning. Whoa, that was loud. Good morning. All right, before we start, Nick wants to remind us of the SI sessions and also remind us what SI sessions are for. So, Nick?
Hello. So, just remind you how exist. Exhale coming up in a week or two here. So, much better to start studying early for that rather than trying to cram the night before. I know from experience, not fun. But yeah, up on the screen are the times for the SI sessions. I've got 3 throughout the week, and Brittany, the other SI leader, has 3 throughout the week as well. And SI sessions are not really places to go to get help with specific questions on homework. We do interact with you guys to help get you some hands-on work with the course material so you're better prepared for your homework interested, definitely show up. We'd love to have you guys.
Hey, thank you, Nick. Okay, so please do attend SI sessions if you feel like you need a little bit extra help in understanding the course concepts, materials, and stuff like that. And Nick doesn't get paid if you don't show up. So, no, I'm just kidding. He gets paid no matter how many people show up. So please do show up and make him work. No. Nick is a very good guy. He'll help you get a good grade on the exam. Right, Nick? Okay. All right, so today we're going to look at, forgot what this section is. Let me look up the section number. 2.7, sorry. Section 2.7, excuse me. We'll be looking at these things called derivatives. And how they relate to the rates of change. I'm going to revisit the tangent line and secant line problem we investigated earlier. So once again, I'm going to sketch just a pretty general function here. So let's have one that looks something like a parabola. Okay, so this is point A right here. Now remember, our goal is trying to find out the slope of the tangent line, right at x is equal to A. So that green line right there. Okay, we'd like to find out what the slope is. And because the slope can tell us a lot about the function, and there are many, many applications using the slope. So that's the ultimate goal here. Now if x is equal to a, then the y value is obviously f is equal to f of a, right? So that's a comma f of a. All right, so we can't find the slope right now. But remember, we use the secant line to approximate that. So let's pick another point. And that point is allowed to move about. So we're going to say it's at x is equal to x. And y is equal to f of x. Okay, remember the idea is to move that second point closer and closer to the first point, eventually approximating the slope. All right, so there's my secant line. And the slope is easy. The difference in y over the difference in x. Okay, none of this is new. We've seen this before. Now to get the tangent line slope, we're going to slowly bring the second point closer to the first. So here's the key words, right? Close to the first one. Of course, we can't make them at the same spot because then the slope is undefined. Okay? And then this thing we're doing here sounds awfully similar to what we have been doing the last few days, dealing with limits. We want something to get close to something else without actually being there. So there's a limit right here. And that's the reason why we learn limits. We had to actually use that to tackle this kind of problem. Okay, now if I could bring x close to a, then we know that the slope of the secant line should eventually become the slope of the tangent line. This thing is also called a difference quotient. But bear in mind that it's really nothing more than the slope. That's all there's to it. It looks kind of strange. It's got a different name, but it's just a slope. You take the limit of a slope, we get what we want. So, therefore, the slope at the tangent of the tangent line at x is equal to a is, take the limit, we bring the second point, that means we're free to choose x. We have the freedom to choose what x is going to be. We want x to get very, very close to a. So we take the limit, making x close to a without being a. And what do we take the limit of? The secant line slope. And now we're going to have a new notation to describe this quantity right here. This thing came from the function f, and it's at the point a. Now to denote that this is a slope, we put an apostrophe right here. It's not really an apostrophe, but it's kind of like an apostrophe. It's called, the way you read this thing, we say f prime at x is equal to a. All right, so that's the way we're going to denote the tangent line slope, using this formula right here and that notation. We also give it another name. We also call this the derivative of f of x at x is equal to a. Okay? Now this looks very strange upon first glance. All you need to keep in mind is this is the slope of a secant line. We're taking the limit, bringing the second point close to the point at which we want to find the tangent line slope of. That's all there is to it. Keep the picture in mind as opposed to memorizing the formula. This is one way to describe that thing. Here's another form. And so I'm going to try to reproduce the same picture. Like that. We're still interested in finding the tangent line slope at x is equal to a. So right here. That is still f of a. And let me sketch the tangent line, the green one, right, something like that. Okay, now if you look at what we're doing here, we're trying to bring the second point close to the first. So another way to describe where the second point is how far it is in relation to the first when it comes to the x-coordinate. So let's say the second point is right here. Now instead of giving it a new label here, we'll just say that it is whatever a is equal to plus some other quantity h. H is the distance between the two x values. And the second point in this formulation will look a little bit more complicated. The point will be a plus h, comma, f a plus h. But what we're doing is still the same. Still going to start with the tangent, the secant line. Slope is the same as usual. The second y minus the first y over the second x minus the first x. A plus h minus a, of course, is simply h. Exactly the same thing, just a slightly different way to express it. And now we do the same thing. We take the limit, allowing the second point to go to the first, get close to it without being on top of it. And so what we're controlling this time is the quantity h. We control how far that h is. That measures how big the difference is. So when we take the limit, we'll take the limit of this thing, allowing h to get closer and closer to 0. So here's the second way to express the slope. F prime of a is equal to the limit h goes to 0 of that. Okay, so we got two different ways of expressing the same quantity. Both of these are equally useful. They both, for certain functions, one might be a little bit easier than the other, but generally there's not too big a difference. And we're going to follow pretty much the same set of steps we follow with limits. We're going to first look at how we get this thing from purely geometric point of view. It can get cumbersome, but for now we'll focus on the geometry of it. And as we do more and more of that, we're going to start noticing shortcuts. And that will come later. So for now, we're going to have to just slow down, focus on the geometry. All right, so let's try those formulas on something. Let's say f of x is equal to x squared plus x. And let's say we're looking for the tangent line slope at a is equal to 1. Okay, now we got a pretty neat shorthand notation for tangent line, f prime at a, where a is equal to 1, right? Now before we do all that stuff, what shape is this? Parabola. Which way does it open? Up. Very good. How do we know? Very good. The coefficient of the x squared term is positive. So that's an upward opening parabola. What's this x doing here? What does it do to the parabola? Could be considered that. But it's, well, here's the way to look at what this x is doing. Let's make a rough sketch of that. With parabolas, it's very useful if you find the x-intercepts, because you know the vertex is halfway between the two. So let's find out the x-intercepts of this thing. Make y equal to 0, and factor an x out of that. So this tells me that x is equal to 0, and x is equal to minus 1. Okay, so what it's doing is it is in a way can be visualized as an up or down shift, but also it changes the intercepts. And with that information and knowing this thing opens upward, that's all you need to sketch it. Here's the intercept at minus 1, here's the intercept at 0, so opens upward. Something like that. Okay, so we're looking for the tangent line slope at 1. 1 is somewhere down here. Let's extend this a little bit. Obviously not to scale, but let's say this is 1, 1, 1. Okay, so that's the tangent line slope we're looking for. The geometry tells me I'm expecting a positive number. So if I work through all of that thing out and I get a negative number, I know it's wrong. I expect a positive number. Okay, so let's try the first one. F prime of 1 is the limit as x goes to 1. I'm looking at the top of the last page. F of x minus f of 1 over x minus 1. F of x is equal to that. Simple. X squared plus x minus f of 1. That's also simple. If I plug in a 1, I get 1 plus 1, I get a 2. So this thing sits up there. Downstairs is x minus 1. So at this point, we're doing nothing different than the limit problem we have been doing in the last few days. That's just a very, very typical standard limit problem. Nothing more to it. But now we actually have an understanding of what this thing is telling us. So usual things with limits. Notice that this goes to 0 over 0 when x gets close to 1, right? 1 plus 1 minus 2, 0, 0 over 0. And remember, that's a universal sign that there's something causing the 0 over 0 that we can either factor out, cancel them, or do other stuff. Right here, the obvious thing is just to factor the top. I want a plus here, so I want a plus 2 and a minus 1. And as long as x is not exactly equal to 1, these two things will always be equal, and they can always be canceled. So, get rid of them. And now when x becomes 1, x plus 2 is a continuous function by itself, so we know we can simply put in a 1, and we get a 3. Okay? I expected a positive number, I got a positive number. So this, at least, it has the right sign. slope of that line is equal to 3. Okay, let's try the same thing, but with the second form of that formula. Okay, same function, but this form right here. This time a is still 1. And in the second form right here, f prime of 1 is limit h goes to 0, f of 1 plus h minus f of 1 over h. And just so we don't forget, the function we're dealing with is this. All right, so then we proceed. F prime of 1 is equal to the limit h goes to 0, f of 1 plus h. Remember, this means you go to f of x, replacing every single x you see with 1 plus h. Okay, so this is my f of x, 1 plus h. Minus f of 1, 1 plus 1, that's 2. And once again, notice that if h were to become exactly equal to 0, this is 1 plus 1 minus 2, that's a 0, over a 0. And again, that's the universal sign that you need to look for something from all of this mess right here that's causing the 0 over 0. Get rid of them somehow. And there's really not a whole lot we can do other than multiplying this out, simplify, and then try to clean this up. Okay? So what do we get? We get 1 plus 2h plus h squared plus 1 plus h minus 2 all over h. 1 plus 1 minus 2, those go away. H squared plus 3h is what's left on the top. And again, it's just a standard limit problem that we have been doing. I'm still getting 0 over 0, but now I know what's causing that. It's h. And I can pull out an h from the top. And as long as h is not 0, those two can go away. And then what's left here, the closer you make h to 0, the closer this quantity is to 3. And of course, we get the same answer as the last one. It's the same quantity expressed differently. We still get the same slope. All right? Okay, once again, we're still focusing on just the geometric picture behind it. So all of this stuff looks lengthy, and of course in practice that's not something you would do every single time. But you still want to develop a good geometric intuition of what you're doing. We will see ways to get the derivative much quicker in the coming lessons, but for now, again, focusing on just the geometry, the slope, and the limit. Any question on this example? All right, so let's talk a little bit about what the derivative tells us. Remember the secant line slope, if we talked about this a while back, if we're measuring the displacement, then the secant line slope gives us the average velocity. And in general, whatever we're measuring, the secant line slope tells us the average rate of change. Velocity is a rate of change of displacement. So in a more general sense, the secant line slope will give us the average rate of change over some interval. The tangent line slope focusing on the limit meaning behind the whole picture means that we're shrinking that interval to a very, very, very tiny interval. In the case of displacement, this tells us the instantaneous velocity, and more generally, it tells us the instantaneous. No, that's not how you spell that. Instantaneous, there we go, rate of change. Okay, again, if you're driving a car, when you look at your speedometer, this is what you see. You are looking at, if there's a function that your car's displacement is graphing, plotting, what you're looking at that precise moment you look down is the instantaneous rate of change or the tangent line slope at that particular moment. Okay? There is such a function even when you're not aware of it. Okay, secant line is average, tangent line is instantaneous. Very often we see the phrase rate of change. Without any modifier, just rate of change. Usually that implies the instantaneous rate of change. Usually we only specify what kind when we're talking about the average. Rate of change by, like when you talk about speed of something, you always implying that you're talking about the speed at that moment. Okay, so let's combine this and the derivative we just learned and apply this to something. An object is tossed straight up in the air and its height in meters. T number of seconds later is h of t is equal to 12t minus 4t squared. Okay? Think about tossing up a baseball, football, whatever, something straight up in the air, and somehow you're able to measure the height at any given time, and you collect a set of values based on the time and the height from the ground. Okay, let's see, what do we want? We want to find no, that's not how you spell that. I can't spell that word. Instantaneous velocity. Find its instantaneous velocity the moment it hits the ground. Okay, so you know what's going to happen. You throw something straight up in the air, eventually it's going to come back down. When it comes back down, right at the moment it hits the ground, we like to find out how fast it is going. It's not zero. It's carrying some kind of momentum downward, right? So it's not zero. Now, after it hits the ground, eventually it'll be zero, but it won't be zero at that moment. So you imagine what's going on here is toss something straight up, comes back down. If you look at this thing right here, we're going to say that t is equal to 0 is when we throw this thing up. We always count, it's customary to count time from the moment something starts. When it comes back down, right now we don't know what that second moment in time is. Okay, so what do we want? In terms of the mathematics we just saw, what we want is the rate, the instantaneous rate of change of this thing, h prime of t. And this t refers to the time it comes back to ground. This missing value of t right here. Which is unknown at the moment. Before we can do anything, we have to know when that occurs, to use either form of the two formulas we saw. So that's the number one thing we have to do. How do we do that? How do we find this time? Set equation equal to 0. Right, because ground means h is 0, right? So if I make this equal to 0, then I solve for t. That's going to tell me at what 2 times the height is 0. So good. Ground is h equal to 0. So we take our equation, make h equal to 0. This, by the way, geometrically is the same as finding the x-intercepts that we did earlier. Exactly the same thing. We're finding the t-intercept. Factor of 4t out of this. So we see t is equal to 0 and t is equal to 3. That's when I threw the thing straight up in the air. So this must be when it comes back down. So it's this value that we want. Make sense? Okay, now we got a time. We know how to find the derivative. Just a matter of picking either form of the two formulas. Like I said earlier, generally there's not a big difference between the two forms. So let's use the first form. We want to know h prime at t is equal to 3. The second form is when we move the second point whose t value is unknown. H of t minus h of 3 over t minus 3. H of t is simply the formula I started with, 12t minus 4t squared. What's h of 3? Should take no time to calculate. Think about the physical meaning of h of 3. 0, yeah. 3 is when it hits the ground, right? So by definition it's 0. H of 3 is 0. You don't even have to calculate it. If you focus on the meaning, the physical and geometric meaning behind this, that is the obvious answer. Well, of course, if you plug in 3 into here, you will get 0. Okay, we still get 0 over 0, so look for ways to get rid of those things. Take out a 4t on the top. Okay, remember what to do if you want to reverse the order of one of these two? Take out a negative, right? Let's reverse this by taking out a negative. And once again, now we see what's going on here. What is causing the 0 over 0? As long as t is not precisely equal to 3, these two can always be canceled, and we will. All right, so what do we get? We get negative 4 times 3, right? Minus 12. What would the units be? What unit are we using to measure the distance, the height? Meters, and time, seconds, right? So meters per second. Why is it negative? Right. So this negative sign right here, as usual, we define y to be positive upward. That's usually what you would do. In certain cases, if you're tracking something that's falling, like if you're going skydiving or something, you're tracking your position, your height, as you fall towards the ground, you may want to make y negative down. But those are not the usual thing that we typically do. Typically, we make y positive upward. So this negative sign, the negative velocity means whatever this object is, it is traveling downward. The physical picture behind this whole problem we're doing makes sense, right? The thing's coming back down. So it's coming back downward at 12 meters per second. So here's where velocity and speed are different. Speed is always a positive quantity. Speed by itself doesn't tell you direction. If I say I'm going I'm going at 70 miles per hour. You have no way of knowing which way I'm going. Now, if I'm saying velocity is giving some kind of direction information. Minus 12 means we're going opposite to the convention. Normally, upward is positive. Speed is 12 meters per second, but velocity is minus 12 meters per second. Questions? Okay, let me add another part of the problem, another question to this problem. Okay, so we found out when this thing hits the ground and how fast, with how much velocity it hits the ground. Let's find out what the maximum height is. Okay, for now, we're going to use purely geometric ways to figure this out. Now, later on, you'll see that this derivative thing can be used to answer this kind of question very, very quickly and very, very conveniently. Again, for now, focusing on the geometry. We know we hit the ground at 0 and 3. And the equation h of t, 12t minus 4t squared, this is a parabola. We know that. If you don't like t, change it to x and deal with it. Same thing, right? The negative coefficient tells me it opens downward. And t equal to 0 and t is equal to 3 are in terms of the picture behind that, are the t-intercepts. All parabolas are symmetric with respect to the locations of the intercepts and the location of the vertex. The vertex is halfway between the two t-intercepts. That means t is equal to 3 over 2. Okay? And that, in terms of the picture, if you start at 0, you hit the ground at 3, halfway in between, that's when you reach the maximum height. Make sense? Yes? Good. So this is also the time that maximum height is attained. So we're doing this kind of to illustrate using geometry and physical intuition, the kind of things we have to do. Like I said, later on we'll be using the derivative to do stuff like this very, very quickly, and just kind of want to draw some of that contrast when we see it later. All right, so if I know the time, I know how to find the height. I can find out what it is. So the maximum height must be h of 3 over 2. Is 12 times 3 over 2 minus 4 times 3 over 2 quantity squared. So what's this thing here? 36, 18 minus 36 over 4. Right. So this is what? 9, right? 18 minus 9 is 9. 9 meters. By the way, what would the velocity be at that point? Yeah, why is it 0? Exactly, yeah. You could use the formula to figure out that do the long way and use the formula to figure out the velocity. But again, using physical understanding, on its way up, velocity is positive. On its way down, velocity is negative. There's a switch from positive to negative, which is 0, right? That's where things switch. Where does it switch? The moment you hit the maximum height. Okay, so again, you can do this using the formula, or you can just use basic physics to explain that. All right, that's it for today. See you Wednesday.
Yes, sir, I didn't understand this. Like, f prime is 1. I don't get this. Why did you use 1 in the first place?
Because I want to know what the tension on the slope is
At this point. Okay. That I was confusing. First form, second form are one of the two types that you showed us before, right?
They're the same.
What's covered for today's practice?
What's covered? What they will do is they will take an old exam from a past semester. I don't know which one precisely, and just give it to you. The point is not really to do well on that exam. The point is to go through the process and see how it feels before you take the real thing next week. So don't worry about what's on the exam and all that. Just soak up the atmosphere and see what feels like. Hi.
When do I know which one should I use, which formula of the derivative?
Either one.
Either one,
Either one.
always.
Either one. You make a choice.
Okay.
I was confused on the first example problem, how you're getting two.
First example.
You're getting the minus two. I'm confused on how you got that.
Okay, so that's f of 1.
Alright.
So here's my function,
Yeah.
and I put in a 1.
Oh, just putting.
Right.
Alright.
This is what this is.
Okay, that makes sense.
For the exam one, so what sections do we have to like? What questions can we do like from which sections?
The exam next week,
Oh yeah,
it covers the first 10 lessons.
10 lessons.
And if you look at the calendar on the course webpage, it tells you what will be